There's the QMMU, the Quantum Memory Management Unit.
Like the memory management unit in a classical computer.
Very similar. So in a classical computer, the MMU manages the allocation of RAM
Right.
to different processes. It uses something called virtual addresses. Well, the QMMU does the same thing, but for qubits.
Oh.
It creates a virtual quantum memory space for each process.
Hmm.
And it translates those virtual qubit addresses used in the NetQ ASM code into the actual physical addresses in the hardware.
So it's like a mapping system.
Exactly. And this gives the system a lot of flexibility. For example, down the line, it could let us rearrange qubits in the physical memory, or even run QNodeOS on top of a quantum processor that uses error correction.
Where a virtual qubit might actually be multiple physical qubits.
Right.
That's really smart.
It is. The second mechanism is something called entanglement request sockets. These are inspired by the concept of classical network sockets.
Okay, I'm familiar with those.
Yeah, so those manage the connections between processes on different computers on a network.
Right.
Well, these entanglement request sockets do the same thing, but for quantum connections. So when a user process wants to get entangled with a process on another node, it makes a request through the network process, and an entanglement request socket is created.
To keep track of that specific quantum connection.
Exactly. This lets the system keep track of different entanglement requests going to different pairs of processes.
So the QMMU handles the local quantum memory, and these sockets manage the quantum connections across the network.
Precisely. And that allows multiple applications to share the quantum resources effectively.
So that's how QNodeOS is structured. Now the big question, does it actually work?
Right. Well, the researchers did two main demonstrations to show that it does.
Okay, tell me about them.
The first one was something called a delegated computation. Okay, imagine a client asking a server to do a quantum operation for it. It's a very basic form of quantum computing, but it's important.
Right.
Because this wasn't just a pre-programmed experiment. This was the first time an arbitrary quantum network application written in high-level software was successfully executed on actual quantum processors.
Wow.
Yeah, and they showed that the result of the computation had a fidelity higher than what you could get with classical methods alone.
So that proves QNodeOS can handle those interactive applications.
The ones that use entanglement, those millisecond-scale memory lifetimes, and classical communication.
It all worked together.
It did. They did note that the fidelity wasn't perfect, mainly because of noise in the entanglement and some decoherence while the server was waiting for messages. But they also found that the classical processing was actually the bottleneck.
So there's room for improvement.
There is, definitely. But even in this basic form, it showed that you could run a distributed quantum application using high-level software, all managed by QNodeOS.
That's a huge achievement.
It is. And then the second demonstration was all about multitasking.
Okay, what did they do?
They ran two different applications at the same time.
On the same node.
On the same client node. One was the delegated computation we just talked about.
Okay.
And the other was something called local gate tomography.
What's that?
It's a way to measure how well quantum gates perform. Now, the client node only had one qubit. So the idea was to see if running both applications would mess up the results of the tomography.
I see.
And it turned out it didn't. They saw the instructions from both applications being interleaved on the Q device, and the tomography results were the same as when it was run by itself.
So QNodeOS was able to manage both applications without any conflict.
Right. And they even scaled it up, running multiple instances of each application simultaneously. And they saw that the Q device was being used more efficiently. It was spending less time idle.
That's great, really squeezing all the performance out of that quantum hardware.
Exactly. So it shows the real benefit of QNodeOS in making those quantum resources go further.
That's amazing. So what's next? What are some of the future directions the researchers are looking at?
Well, one thing they want to do is to put the CNPU and QMPU on the same board with shared memory to cut down on those communication delays.
That makes sense. They were a bottleneck.
They were. And they also see QNodeOS as a platform for distributing quantum computing programs across multiple processors connected by a network.
So like a truly distributed quantum computer.
Yeah, that's the idea. But Maybe most importantly, they highlight that QNodeOS opens up a whole new area of research in computer science.
In quantum network programming.
Exactly. Things like developing new scheduling algorithms specifically for these hybrid systems, new ways to compile quantum network applications, even new programming concepts to make working with entanglement easier.
It's not just about the hardware anymore.
No, it's about building the tools and knowledge to use it effectively.
It feels like we're witnessing the birth of a whole new field.
We are. It's a shift from ad hoc experiments to a truly programmable platform for quantum networks, and that has huge implications for the kind of applications we'll see in the future.
It's that moment, isn't it? Moving from those carefully controlled experiments to a system where anyone can build and use these applications.
Yeah,
It's like the early days of the internet all over again.
it really is. And it makes you wonder what kind of impact this will have on society. What new applications will emerge as this technology matures?
I mean, will we see things like truly unhackable communication networks?
Or fundamentally new approaches to distributed quantum computing?
It's exciting to think about.
It is.
The whole new frontier to explore. Well, thanks for diving deep